In this video, we will cover the face triangulation process. Quad meshes or 4-point surfaces are not always planar. Most of the quad faces generated in the previous chapter are non-planar faces. This leads to minor variation in the unrolled geometry, which ideally should not happen. Triangular faces, on the other hand, are always planar. Hence, triangulating quad meshes before unrolling is an effective method of ensuring proper unrolling of strips, without geometrical deviations. Let's understand the logical workflow before we start building the script. First step in this process is the grouping of identical quads from warp weft strips. Once grouped, these quads will be triangulated to ensure that both quads have the same diagonals. Slots for cables ties will be created by intersecting extruded rectangular profiles crossing through both quads of the same group. Once we have the triangular faces with slot profiles, the triangles will be clustered as per the original warp and weft strips. Let's start building the script. You may open the Grasshopper reference file to follow along. The first step is to convert the quad faces into meshes using the simple mesh component. In total, both warp and weft strips contain 1024 faces each, which are distributed among 48 branches of either 16 or 32 items. Simple mesh component should give us the same data tree. Flatten, and merge both warp and weft data trees. With warp faces as the first input, and weft as the second input. This should give us a list of 2048 quad faces. Index 0 to 1023 of this list are warp faces, and index 1024 to 2047 are weft faces. Use face boundaries functions to extract the mesh boundary as a polyline. Extract the center of these polylines using the polygon center component. Collect all center V output into a single point container. Use point groups to group these points in pairs, based on distance threshold. This distance threshold is carefully chosen to be small enough to form pairs and large enough to avoid groups with only single points. Since these are almost identical quads separated by 0.5 mm, we can set the distance threshold to 5 times the material thickness, 2.5 mm. The output from point groups should give us 1024 branches with 2 items in each. Any deviation from this data structure means that the distance threshold is incorrect. Point groups component also provides us with the list of indices in each branch. Read the output in a panel. Each group has one index number between 0 and 1023, representing warp faces, and other index number between 1024 and 2047, representing weft faces. Sort these indices such that warp faces occupy the first index in each branch. Use list item to create a list of mesh faces based on these indices. Now we have mesh faces grouped in pairs, with the first index belonging to warp strips. Use list item again to separate these lists into a list of warp and weft faces. The difference between these lists of warp and weft faces, and the previous list is that these are coordinated via index. That means that one index in each list represents the pair of quads, like this. At this point, we must also store the numerical indices from point groups into a numeric container. This will help in reorganizing the quads as per individual warp and weft strips. Let's highlight this numeric container to be used later. The next step in this definition is the triangulation of quad faces. Use face boundaries to extract the boundary polyline of each face. Use the discontinuity component to identify the vertices of warp faces only. This gives us a list with 1024 branches, and 4 points in each branch. Now sort these points using the weft boundary polylines as guide curves. Bring the sort along curve component into the canvas. Connect points output from discontinuity into the points input of sort along curve, and the weft face boundaries into the curve input. Create a closed polyline from the sorted points. Now we have two lists of boundary polylines aligned, with the same start and end points. For the triangulation definition, use the discontinuity component again to extract the vertices of each polyline. Use list item, and extend the number of outputs to 4. Merge output 0, 1 and 2 in one merge component. and merge output 2, 3, and 0 in the other merge component. Order of merging is important because these vertices will define how the triangular mesh is constructed. Use construct mesh component to construct the triangular mesh. Connect the merge output into vertices input. Set the face input to t, open curly bracket, 0, semicolon, 1, semicolon, 2, close curly bracket. Do the same for the other merge component as well. Copy the construct mesh component, and connect the second merge output into the vertices. The Rhino viewport displays the triangulation result. Merge both construct mesh outputs, and store them in a mesh container component. This is a list of 1024 branches with 2 triangular meshes in each. Group these sequence steps, and name it Triangulation step. Copy this group below, and change the input quad meshes from warp to weft. The Rhino viewport displays the triangulation result where each pair of quads is triangulated in the same direction. Try building the definition till this point. Ensure that all pairs of quads are triangulated in the same direction. In the next chapter, we will cover the workflow and definition for creating slots in these triangulated mesh faces.